Hello, hello, and we are back to topic 4, applications of derivatives. Last class, day 37, we covered the EVT, the extreme value theorem, which really is just a nice excuse to introduce some new vocabulary: absolute maximum, absolute minimum, relative or local, maxima, minima, all that fun stuff. We covered what absolute extrema were last class, but we didn't really talk about how to find them. And actually, that's really going to be our next few days. Today, we're going to discuss how to actually find absolute maxes and mins. And then the next couple days are really going to be dedicated to how to find and identify local maxima and minima. However, we're going to keep refreshing your memory on what all of those are. So you should have a textbook around you, or you can use a digital copy. And you can please read the paragraph on the bottom of page 249. It's entitled Local Maxima and Minima. And although there is a next page 250, I would say don't go on to that. Just briefly read the bottom. It's going to remind you what those local extrema are. And then second, if you turn to page 253 and do problems 15 through 18. And I've kind of set up 15 through 18 down here so that you can write your answers on here. But the book has some nice graphs, and they took up a bunch of space on this, and I didn't want to do that, so there is the space. Once you're done with that, definitely check 15 and 17, the answers in the back of the book, right? All the odds are there. We will go through 16 together at the end, though, just to make sure that, that you understood all the parts. Okay, go ahead and pause me. Let's see what you can do. And we're back. I did say we'd go through 16, so we should probably do that. Scooting over to 16, I have it redrawn here with my masterful artistic skills, and they're asking us about a bunch of points on here, and I'll probably go through and zoom in and then highlight these points in orange. I'm not going to name them. They're all over the place in terms of names, but it looks like there are 1, 2, 3, 4, 5, 6, 7 points here. Let's see what we can do with this. Why don't we start with relative maxes and mins, because I think that one is something new for today, and then we can talk about the absolute. Oh, let's do absolute max and mins first. Easy. Absolute min, it's the lowest point. Absolute max, it's the highest point. Great, we crushed those. I'm proud of us. Remember, those can also be called global maxes and mins, but absolute I found is a little more common. Okay, relative max and mins. We'll start with relative max. Relative max, relative max. Relative min, relative min. Now remember, or this might be new to you, in order to be a relative min or a local min, you need to be relatively lower than every point, in quotes, nearby, end quotes. So if we look at this point down here and we think about a couple points on the left and a couple points on the right, is that yellow point lower than all the rest? Certainly, so it is a relative min. All right. However, if we look at this guy over here, this guy is higher than the ones on the left, but lower than the ones on the right, so it cannot be a relative min or a max. This would be a neither. What about this end point over here? Because this end point is certainly higher than all the points on the left. So is this a relative max? And it is not. Our definition for a relative max or relative min is it needs to be relative to both sides. And since this is where the graph ends, there is no other side here. It can't be a relative max or min. Relative maxes and mins cannot occur at endpoints, at least with the definition we're using. So although this is lower, it is not a relative min, it's only an absolute min. This point up here is both an absolute max and a relative max. And I think that probably clears just about anything up, or everything up, so let's go ahead and jump back to this. Your next goal is to basically work backwards. Now we're going to give you where all of these things occur, and you're going to have to sketch a graph. Now this is a little challenging the first time you do this, especially dealing with this f prime of x equals 0. So I'm actually going to skip back to 16 really quickly to show you the spots where f prime of x equals 0, and then you can try these. So back to 16 again, and I'll erase these extra circles. Let's identify all the spots where f prime is 0, because visually we haven't done a ton with this yet. Remember, if f prime is 0, that means a horizontal tangent lies perfectly flat with these curves. So this would certainly, and I'm just going to circle the spots in purple that have a slope, a derivative of 0. There's one here, and one here. Additionally, there's one over here. right? Notice that this tangent line does come in, lies flat, and then goes straight back across, only touches at that one point, and it does lie parallel to the graph. If you zoom in, they do appear, that local linearity, they do appear to be parallel at that spot. So there are actually 4 places where f prime of x equals 0. And just as a bonus spot, what about where f prime of x does not exist? Well, there are actually 3 spots on this graph where the derivative where f prime of x does not exist. The most obvious down here is this pointy point. Of course, we would not use pointy point. We would say probably where the limits of the derivatives are not equal to each other. But then there are 2 other places. Can you guess them? Well, they are, of course, the 2 endpoints, because there is no derivative on the right side, so the limits of the derivatives cannot equal each other. There is such a thing as a one-sided derivative, but we're not going to cover that. Your book does cover it if you want anything, but we're not going to go through it. All right. Let's take a peek. You should definitely try this one on your own. However, if you want to listen through because it's the first time we've done it, that's fine. We're going to be sketching graphs pretty much every day for the next 10 or so classes because that's a really nice way to cement or concrete into your brain what all of these ideas are talking about. Now, how do I do it? Well, I'm going to do this first one in purple, I think. F prime of x equals 0 for x equals 1, 2, and 3. So here are 1, 2, and 3. If the slope is going to be 0, and notice they didn't really tell us where everything is, all that's telling me then is that there is going to be some sort of like smooth curve there, either like this or like that. It could also look something like this. So we're going to come back to that one, and maybe let's go ahead and do the absolute minimum first. F has an absolute minimum at x equals 1, so that's going to be the smallest point. It has no local extremum at 2, so that can be anywhere on here, and it has an absolute max at 3, so that's got to be somewhere high up here. What is this going to look like then? And we're also going from 0 to 4 closed interval. Well, the closed interval part should be pretty easy. I'll do that one in which color I haven't used blue yet. They didn't tell us anything about 0 and 4, so I'm just going to put, it doesn't even matter where, I'll just put a little point here and then some other point over here so we can see the starting and ending, and they're closed circles because 0 to 4 is closed. We're going to start with the absolute minimum at x equals 1, so I'll do that in yellow. Absolute minimum at x equals 1, well, that's got to be the lowest point, so I'm just going to go ahead and kind of put in just a little line here to remind myself the slope or the tangent line needs to be 0. No local extremum at 2, but the slope is 0. So somewhere at 2, I'm going to go ahead and put a little line here, just to remind me, and I'm just picking these y values randomly, it doesn't matter. And then the last one, local or absolute max at 3. So absolute max at 3 is going to be, it doesn't matter, I'll put it all way up here if we want. I think we probably have enough to build our graph now. To build this graph, we are going to drop down. We have to make it nice and smooth to show that it is a slope of 0. Here to get a slope of 0, we're going to come flat and then continue up, right? We get that slope of 0, and then we're going to come up here, curve, and come back down. And I think this graph would fit all of our requirements. There's an absolute min, absolute max, and then no max or min right here. Easy to it, nothing to it. Second one, I think you guys should probably give this one a shot, and then we will come back together shortly. Hopefully you did all right with this. Similar idea, let's kind of go through each piece here. There are 3 spots where the slope is doing something interesting, so we'll come back to those. There's an absolute max at 2, and it also says 2 is undefined. A lot of times when I do something undefined, I just like to make a sharp point there. So at 2, it's an absolute max. I'm just going to make it look like that. And that'll just remind me that it's no slope there, but either way, it's still an absolute max. Okay. Neither a max nor min at 1, but 1 has a slope of 0, so I'll just kind of throw something like this. And then an absolute min at 3, okay, absolute minimum at 3, so we'll do something down here, also a slope of 0. And then I think that probably just about covers it. They did also tell us that we're going from 0 to 4 again on this closed interval. We'll pick the same endpoint this time, why not? Something like that. So I think my graph is going to go up here, nice smooth curve, neither a max nor a min, and it's going to connect up over here, sharp point, okay? And then actually maybe I'll kind of curl it down here, and then this one's got to be something like this, and then back up over here. Nice. And it is kind of hard to make a sharp point here, so maybe you can even go like that and just have it point the other direction. There we go. That looks pretty good. Nice. Okay. No slope here, but it is the absolute max. Now, it's pretty easy to define an absolute max or min. You can describe it visually to your group, nothing too terrible. However, it's a little bit harder to explain what a relative extrema is. So if you're working in a group, try that right now. Imagine you're talking to a 5-year-old, and you wanted to explain to a 5-year-old what an absolute max or absolute min was. Shouldn't be too hard, right? You just tell them. It's the biggest point, it's the tallest point, it's the shortest point if you're doing absolute min, right? However, if you're explaining what a local extrema is, that's a little bit harder to put into words. A lot of people tend to say, oh, it's like when it like curls back up around, and you're kind of right, it is when it curls back up around. But yeah, it's pretty tricky. And so once you've jotted down your ideas, we're going to again discuss what we're doing for the next few days. So realize that day 37 didn't actually have anything to do with calculus. The extreme value theorem said closed and continuous. There's no calculus there, right? Calculus has to involve a limit, a derivative, or an integral. So what we're going to do today is have an idea of how to use calculus to define absolute extrema. And then over the next couple days, we're going to work on using calculus to define relative extrema, because it turns out that's a little bit harder. Now, let's go ahead and back to the opener. We're asking if f of x has a local max or min, what has to happen? So taking a peek at this, look at these local maxes or mins. There are only 3 of them. And what is in common to all 3 of those? Well, you might notice that for all 3 of those, the slope is 0, yeah? Oh, wait, I lied. There's a 4th one, isn't there? Look at this guy down here. He almost got away. And for there, the slope does not exist. The derivative is probably what I should say. So it seems like at these local maxes or mins, the derivatives don't exist. And that is a way to start to define it, right? So if f of x has a local max or min at some location, then f prime of that location must equal 0 or be undefined. D&E, if you will. Is the opposite true? So if I said, please go ahead and find all the places where f prime is 0 or f prime does not exist. Okay, well, we go back up here and we're like, all right, and we'll erase these confusing pieces and I'll keep my colors going. F prime is 0 in 1, 2, 3, 4 spots, and f prime does not exist at this spot down here. So I see 5 places where f prime is 0 does not exist. Are all 5 of those relative maxes or mins? This point is not. So it seems like the reverse of that is not true. So we can't say that a point is a relative extrema if and only if the slope is equal to 0. Because if and only if means we can go the other way too. So if we say the derivative is 0 or undefined means that there's a relative min or max there, it is proved incorrect by that point near the end. Well, I don't think, so let's see, blah, 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 blah. Okay, it said we should do a sketch. We can just do the same sketch that I did before, right? We can just do something like this, yep, and we can say that has a slope of 0, but it's not a critical point. Okay, so what else has to happen for x equals c to be a relative max or min? Well, that's something for you to ponder, and we're going to go more in depth with that over the next couple of days. Maybe you were able to come up with a good answer, and that's awesome. Hold it in your head. We're going to come back to the idea of relative mins and maxes, and instead for today, we're just going to focus on what we call these places where f prime of that value is 0, or where, and this should probably be c down here, sorry, or where f prime of c does not exist. Okay, so let's use some cool mathematical notation. Given that c is an element on an open interval, so essentially if you ignore the endpoints, and c is some value between the endpoints of an interval, then if f prime of c is 0 or f prime of c does not exist, we say the point c comma f of c, the actual point on the graph, is a critical point. And I will actually make the argument that today is, pun intended, the most critical of all days of this unit, because understanding what a critical point is and how to find it, and then at the end of today, how to actually find absolute maxes and mins really is it's such an important foundation for the rest of this unit. So make sure we focus in and make sure we're comfortable. All right, find the critical points for each equation. Then use your calculator to graph the equations and decide if your critical points correspond to relative mins, maxes, or neither. All right, cool. Critical points, how do we start? Step 1. We need to find the derivative, because ultimately a critical point is where the derivative equals 0 or does not exist. Okay, derivative of this, before I take the derivative, I always like to rewrite this. Your book really loves this notation because it takes up slightly less space than writing it like this, right? But I always like to write it this way. All right, derivative time. 3 comes down, 3 times 3, 9x squared. All right, the 2 comes down, and I think it's going to cancel with the 2 over here, won't it? So it just becomes plus 3x, and then this guy becomes minus 2. All right, looking pretty good so far. I mentioned this yesterday, but you're really going to want to get in the habit. If you take the derivative and it's pretty easy to simplify or factor, you should start by doing that, because almost always for the rest of this unit, when you get a derivative, you're going to either be setting it equal to 0 or some other number. And so you're going to have to solve it, which almost always involves factoring in this case. So I'm going to go ahead and factor this. We covered factoring last class. I'll do just a quick guess and check. I always like starting with the ones in the middle, 3x and 3x. I'm trying to make 3 when I multiply everything out, and I know the ends have to be negative 2. So I'm probably going to do plus 2 minus 1. I think that's going to work, because this gives me 6x. And this subtracts 3x off. 6 minus 3 gives me 3. Great. Guess and check. We crushed it. I'm very proud of us. Find the critical points. Well, there are 2 criteria we have to check every time we look for critical points. And I always like to make just a nice little like T-chart or 2 columns, whatever sounds good to you. The first thing I like to say is that a critical point occurs when the derivative becomes 0. Easy enough. We know what the derivative is called. The derivative is called 3x minus 1 times 3x plus 2. And when I say what it's called, I mean what it's defined as. It's very important to state what you're doing first before you skip right into setting the derivative equal to 0. Oftentimes, on a free response, if you're asked to find critical points, you get a point for doing this, but not necessarily this. You're trying to show them you want to find where the derivative is 0. And although setting this equal to 0 is saying the derivative is 0, I always think it's a great idea to explain what you're trying to do at the beginning. I mean, if you'd factored wrong, this would be wrong. Okay, once we're here, we make our 2 equations, all right, 0 product property, and then do a little mental math. We end up with x is 1/3, or x is subtract 2 divided by 3, negative 2/3. Cool. Found those 2 critical points. But we have a second part we need to consider, and that is, where does y prime not exist? Now notice I didn't put equals, because equals we only use with values here. So we're saying y prime does not exist where? Well, this is a polynomial, and polynomials exist. They are continuous everywhere. So we really don't have to worry about this does not exist with polynomials. That's pretty nice. You could put a little slash here to say the empty set if you wanted, which means there's no solution. You could say no solution, or if you realize that never happens, you could even just cross it off, right? If it's crossed off, it doesn't matter. But the only solutions here are these 2. I tend to put no solution after just so I know that I considered it too. All right, we found the critical points. We found where y prime, or the values that make y prime equal to 0 or y prime not exist. Is that it? No, it says use your calculator to graph this equation and decide if your critical points are relative mins, maxes, or neither. Because at this point, I don't know what these are. This is just places where the slope is 0. So I'm going to go ahead and pull up the graph because I have that ready for us. Look at me being prepared. I'm so proud of myself. Here's the original equation. I'm not graphing the derivative. We haven't done that yet. I'm just graphing the original equation here. Then I'm going to zoom in on this, and let's take a look. Here is a relative max. That is where the slope is 0, and I just found where the slope is 0. If we look at this point, negative 0.667, I think that's negative 2/3. So negative 2/3 is a relative max. Oh, good, we found that. So x equals negative 2/3 is a relative max. We're not explaining how we know that. We don't know how to justify that yet. We'll do that next class, but that's easy enough there. And then same thing, wonder what x equals 1/3 is. It's going to be something else that's relative, I think, in this case, so it could be neither. Oh, look at that, 1/3. This is a relative min. Nice. Doing well so far. Nothing too hard. All right, let's look at one more. F of x equals x squared times the natural log of x. Two things that are first, natural log, and second, multiplication. Product rule. Here we go. F prime of x first. Product rule, 2x, keep natural log the same. Add on x squared, take the derivative of natural log. Can we simplify this? I think we actually can, and I mentioned wanting to simplify if at all possible. So we have 2x times the natural log of x plus, and then x squared times 1 over x isn't going to cancel one of the x's here, so I think it's just plus x. And actually, let's go a step further. I see that each term has an x in common. We're going to factor that out. 2 natural log of x plus 1. Nice. I think that's about as simplified as we can get, so let's get down to our critical points. And you can label it too if you want. A lot of times people label critical points as CP or CPs just to show you that that's what they're trying to find. You do not have to do that, but it's never a bad idea. We again need to check two places. Where is f prime of x equal to 0, and where does f prime of x not exist? I'm actually going to start with where f prime of x doesn't exist because there are cases here. And that is, of course, because of natural log. We need to remember three key things about logs, or really natural log in general. First, you can't take any log of 0. Second, okay, you can't take the log of any negative number. And third, you really want to remember what undoes each kind of log. So in this case, natural log and e make 1. You might even argue that there's a fourth one, remembering that any log of 1 is always 0 too. But the two big ones for us is that we're not allowed to do the log of 0 or negative numbers. And since we have a log in here, that means that x cannot be 0, or x also can't be less than 0. Okay, and we could probably put all of that together by saying less than or equal to 0 is no good, right? We're not allowed to have that. So just keep that in mind. Now, this is different than what we saw on 16 earlier, right? Or even something like this. This point right here would be a single point that we aren't allowed. This point right here, it's a sharp point. That's a single point that we wouldn't be allowed to use in the derivative. However, what we found on this one is not a single point. What we found here is an interval. And if an interval isn't allowed to be used, that probably means the graph just doesn't exist to the left of 0. In fact, it doesn't exist to the left of 0. So just keep that in mind when we find this f prime of x equals 0. Okay, f prime of x equals 0, well, we're going to replace f prime of x with what it's equal to, something like this, and then make two equations, x equals 0, or 2 ln of x plus 1 equals 0. I don't think there's too much we need to do with x equals 0. That one looks done to me. So we get 2 ln of x equals negative 1. Divide by 2, natural log of x equals negative 1/2, and then remember how to undo natural log, and that's where we do e to the power of both sides. Okay, and that finishes us off with x equals e to the negative 1/2 power. Right? If you wanted to write this a little bit further, you could say it's 1 over the square root of e, if that makes you happier too. Either one is fine. I would probably stop earlier. Okay, great. So we found those. Is there anything wrong with any of those? Well, notice that x equals 0 wouldn't actually be on the graph. The original graph has natural log as well. 0 doesn't even exist there. So you could still argue that it's a critical point. But since our graph won't exist over here, a lot of times if you get a critical point that's on the part where the graph doesn't exist, they won't classify it as a critical point. You can still put it. They're not going to mark you as wrong. So let's see what these two show up as, both x equals 0 and x equals 1 over the square root of e. Okay. So let's turn off this graph, pull up the next one. And as expected, notice that the graph stops right at 0. It even says that 0 is undefined, right? There is no point there. And two things to know. First, if there's no point, it can't have a slope. Second, if it's an endpoint, which it is, it can't have a slope. So it doesn't surprise me then that this is a critical point. There is undefined slope there. Okay, and then there's no graph over here because you can't use negatives in the logarithmic equation. And then let's take a look at this relative min down here, 0.607. Well, guess what happens if you put this into your calculator? It is approximately 0.607. And this is a relative min. Yay! All right, now it's wonderful that we can find critical points and endpoints, or critical points by setting the derivative equal to 0 and finding what the derivative is undefined. However, our main goal for today is not only to determine where the absolute extrema are located, but also what are their values. Now, all we did so far is we found some critical points, and sometimes they're absolute mins, absolute maxes. In fact, this one over here is an absolute min and a relative min, isn't it? But what we're going to attempt to accomplish by the end of today is we're going to start ignoring those relative mins and maxes, again, a little bit more challenging, and we're just going to say, are we able to figure out where the function is largest over an interval and smallest? So we're going to start with the equation f of x equals x to the fourth minus 2x cubed over this friendly interval. So first question, is it guaranteed that f of x will have an absolute max and min? I mean, why would we bother doing a problem to find them if they don't have it? Well, hopefully you're saying, yes, we learned this on day 37. This is the extreme value theorem, right? So we would say something like, as f of x is continuous, and we don't want to blindly go into this, is f of x continuous? Oh yeah, it's a polynomial. There's nothing that will break this, so that's good so far, right? As f of x is continuous on, and we need a closed interval, on -2 to 2, that is a continuous on a closed interval, then the EVT, I'm going to be very lazy here, guarantees, watch my laziness, that. Easy. Now that is literally what I would have written if it's a real test, but it's not, and we get the idea. Cool. B, find the locations and values of the critical points on the given interval, then label them as either the absolute max or absolute min. Okay, well, why are we doing this? Well, we might remember from earlier that those relative maxes and mins, I mean, even think about this last problem. This was a relative min and ended up being the absolute min. So I think maybe if we find these critical points, and then whichever one's the biggest is probably the absolute max, and the smallest is the absolute min, that seems like a thing. So let's go through it. We have f prime of x first. Ooh, color changing. 4x cubed minus 6x squared. Again, factoring if possible, we can take a 2 out of both of those, and an x squared, I think. 4 divided by 2 is 2, x cubed, taking out the x squared is still x. 6 divided by 2 is 3, and we took out the x squared, so I think we're here. Okay. Hopefully we can see, looking at this, that there are no places where f prime of x is undefined. It's a polynomial, it's always defined. So when we find the critical points, I think the only thing we'll need to do is set our equation equal to 0. The derivative equal to 0. And so that gives me 2x squared times 2x minus 3 equals 0. And then we have to make two equations. So first equation, 2x squared equals 0. The other equation, 2x minus 3 equals 0. Hopefully you can see you divide by 2, take the square root, you get 0. Add 3, divide by 2, we get 3 halves, 1.5. Nice. Now, it did say find the locations and values. Well, what we found then is we found the point 0 comma something, and also the point 3 halves comma something. Now, this is the part that people get tripped up about. They want us to find the values of the critical points. That does not mean plug the critical points into the derivative, because we know what's going to happen if you plug the critical points into the derivative. We set the derivative equal to 0 and solved. These are the points that make the derivative equal to 0. We are not going to plug them in there. These points over here need to be on the graph of f of x. We want to know on the actual original graph, what are the y values? Well, I think we should probably just go through and actually plug them in, right? So we're going to take the original equation up here, Yeah, and we can do some mental math. The first one I think is quite easy. We're going to find f of 0, right? This guy over here, and that's just 0 if you plug everything in. Cool, 0, 0. The second one is 3 halves, and this one might be a little bit scarier, 3 halves, but I think we can work through this. 3 halves to the 4th power minus 2 times 3 halves to the 3rd power. Okay, we got this. I'm excited. So 3 to the 4th is 81. 2 to the 4th, 2, 4, 8, 16. How do I know 3 to the 4th and not 2 to the 4th? Because the world be weird. And then this is 2 over 1. This is 27 over 8. Okay, and I'm going to simplify this. This becomes 1, and that becomes a 4. Now to turn 4 into 16, let's see. I think we need to multiply both of these by 4. 27 times 4, 7 times 4 is 28. That's 108 over 16. How far apart are 81 and 108? That's looking like 27 sixteenths with a negative. All right, so negative 27 sixteenths. And you don't want to box that because that's not our final answer. These guys are our final answers over here. They did ask us to classify these as either the absolute max or absolute min. That's not something we've done before, but looking at these 2 points, this appears to be smaller. Look at that value. And this one appears to be, that one appears to be larger, right? And this other one appears to be smaller because it's negative. So could we say we found 2 critical points, and then this is going to be the absolute min, and this guy over here is going to be the absolute max? Well, maybe. Let's take a look. Sketch the restricted graph from negative 2 to 2. So I think we're going to need something like this. Right? We know we definitely have to go negative as well, so I'll err on the side of going negative and positive, something like this. We know we definitely have the point 0, 0. We also have the point 3 halves. So let's go negative 1, or 1, 2. Nice job. And negative 1, negative 2. We know at 3 halves, so somewhere in the middle, there's this negative 27 sixteenths. 16 times 2 is 32. That's pretty close to negative 2, I think. So we'll just kind of have this point hang out down here for now, and then we'll come back to it. Because for the rest of this graph, I'm definitely going to use my graphing calculator. Okay, I have everything put into Desmos already. Here's my graph. I've done the restriction on Desmos too, if you don't know how to do that. So it's only going to graph from negative 2 to 2. And I'm going to find the values of the endpoints. Oh, 2 is easy. That's 0. Cool. This one, ooh, where is that? Oh, it's way up here. Whoa, look at that point. If I zoom in, it's not even letting me click it, so we're just going to go over here. There it is, 32. So I have to go up to 32. So we'll say that this guy is 32 up here. This one is 0 over here. And then just taking a general look at this graph, it looks like it kind of zeroes out here, zeroes out, and then we've got it. Okay, so it looks something like I would like to pick the page that I picked. Wonderful. It's going to come down here, 0 slope, come down, 0 slope, and then end up over here. All right. Well, were we right? Was this guy the absolute min, and was this the absolute max? And the answer is almost, right? You might notice that this one was definitely the absolute min. So absolute min, just keeping track, occurred at 3 halves and had a value of negative 27 sixteenths. The absolute max, though, is not there. The absolute max is way over here. And so what some people forget about absolute mins and maxes is that they can occur at endpoints. In fact, it actually turns out that absolute extrema occur at critical points or at endpoints. Now, the full process to actually locate absolute extrema on a closed interval is usually known as the candidates test. No, it's not missing an apostrophe. It's putting up all the candidates and testing them. Okay? Now, this test, I say, is used at least once on every AP exam. It's probably more than once. It's extremely common, and it will definitely be there. The idea behind it is we identify all the possible candidates, which means all the possible locations that the absolute max and mins, the absolute extrema, can occur. And then we find all the values that correspond with those locations. Lastly, if we've taken into account all the possible spots where the absolute maxes and mins can occur, then the largest value has to be the absolute max, and the smallest has to be the absolute min. It's very, very similar to what we did over here, right? We found the locations where the absolute maxes and mins can occur, and then we found their actual values. Of course, we just forgot one thing. We forgot to take into account the endpoints. But then that would have given us 4 possible places where the derivative is 0 or undefined, and then the 2 endpoints. And all we do is we find the value for each one, and whichever value is the biggest, absolute max, the smallest, absolute min. Very straightforward process, but very powerful. So running through this without showing you a graph, there are 3 steps. First step, find all the locations of the, small line, of the critical points by setting f prime of x equal to 0, and then solving for x. Nothing too bad. Don't forget to include any values of x that make f prime of x undefined. And last but not least, any critical points that are outside of your interval, because maybe you found like -5, 0, and 2. Well, if -5 is outside of this interval, let's say it's from -2 to 2, then we can exclude that. Step 2, I always make an input-output table. I think it's a really nice way to organize your work. You fill in the inputs with all of your critical values, and this should probably say critical locations, that's fine, and your endpoints. These are your candidates for potential extreme values. Then take all those candidates, evaluate them in f of x, the original equation, to complete your input-output table. Your largest output is the absolute maximum, and your smallest output is the absolute minimum. All right, so let's see this in practice. We have 2 equations to finish off class with today. Nothing terrible. Let's rock and roll. Let f of x equals a graph of the sine of x plus cosine of x. Anyone know what that graph looks like? I don't. Then find the values of the absolute extrema of f over that interval. If you have extra time, check your answer on your calculator. Really your graphing calculator, because we're just going to check it using a graph. Okay, so 3 steps. Step 1, critical points. Let's take the derivative. F prime of x equals, derivative of sine is cosine. Derivative of cosine, any derivative starts with c, has to be negative, so negative sine of x. Nifty. Step 2. Well, I guess we're still on step 1 if we're going with the candidates test up above. So finishing critical points, let's determine where this function is equal to 0 or undefined. Now, visually looking at this, I know there's no value that breaks cosine or sine, so I know this will never become undefined. So I'm just going to go ahead and set this equal to 0. It's a little bit trickier to, we'll say, set it equal to undefined or DNE, because you really have to know a lot about the function. We'll see one of those later on. I will say it's pretty uncommon for the candidates test to include a critical point that does not exist, but it's not impossible. And again, we will see one later on. So f prime of x equals 0. That's where our critical points will occur this time. So f prime of x is the function cosine of x minus sine of x, and that has to be equal to 0. Uh-oh. This is a tricky equation to solve, but it's come up once or twice, so I thought it'd be useful to run through. The way that I like to solve this is I like to add sine to the other side. So it becomes cosine of x equals sine of x, which seems counterintuitive because you're like, now the x's are on both sides. But what I'm going to do from here is I'm actually going to divide both sides by cosine. So divide by cosine of x, and then same thing over here, we are going to divide by cosine of x. And by doing that, cosine divided by itself is 1. And then although you can turn sine of x divided by cosine of x into tangent, that's okay. If you know where tangent is 1, then you can totally solve this problem. However, you might not be comfortable with tangent, so I actually like to leave it like this. Because then it comes out to, okay, well, if we're dividing to make 1, then what that really means is where, ooh, my eraser went crazy there. What it really means is where are sine and cosine the same value? Uh-oh, my tablet's having issues. That's okay. Where are sine and cosine the same value? Because the only way you get 1 is if something divided by itself creates 1. And so if you think about your unit circle really quickly, you'll realize that sine and cosine here, maybe I can zoom in, zoom out, there we go. You'll realize that sine and cosine are rarely the same value, right? This point right here, they're definitely not the same. That's 1, 0. They're 2 very different values. In fact, the only time that they're going to be the same value, if you think about a triangle where we know this is cosine and this is sine, they're only going to be the same as if the two legs, these two guys, are the same size. And so if you picture a triangle, and I'm just going to redraw that quickly. If you picture a triangle where the legs are the same size, then hopefully you remember that has to be a 45, 45, 90 triangle. Sine or cosine of 45, or if you remember pi over 4, sine of pi over 4 and cosine of pi over 4 are either 1 over root 2, or if you rationalize, root 2 over 2. So that is definitely a location where they are the same. So going over to solve this equation, we can say that x is definitely pi over 4, but don't forget we can keep going around. What about 3 pi over 4? I think that won't work because we get a negative and a positive. 3 pi over 4 would turn this into negative 1. 5 pi over 4 would be okay. Then we have a negative and a negative here. Oh, but wait, we're only looking on the interval from 0 to pi, so we actually only get one answer here. That's pretty nice. So we got one critical point, go us. So what does that mean? Well, it really means nothing to us so far, because once we found a critical point, we still don't know if that's an absolute max, absolute min, or neither. What we need to do at this point is we need to set up our candidates test. And our candidates test, testing all the candidates, I always go through and I make an x, and then what do we call this equation? Is it called f of x? Yeah, x f of x table. And there are 3 values in my table. So I'm going to go ahead and separate this like so. The 3 values, well, pi over 4 is certainly in my table because this is where the derivative is 0. However, there are 2 other possible places where the absolute max or min can occur, and those are the endpoints. So I also need to check 0 and pi. All right, well, looking at this then, I think we probably need to find the outputs. Now again, we don't use the derivative here because if you plug this into the derivative, you're going to get 0 every time. That's the whole point of finding a critical point. Not a derivative. We plug this into the original equation because I'm always curious about analyzing the original equation. What's the highest value on the original? What's the lowest? Okay, so we have a little bit of math to do here. The original was sine plus cosine, so this becomes sine of 0 plus cosine of 0. We actually drew that quadrantal angle before. Sine is 0, cosine is 1. We get 1. Actually, while we're at it, let's do pi because that's really similar, right? Pi is just over here, same idea, but it's negative 1 comma 0. Remembering that sine is the y and cosine is the x, that gets us negative 1. Okay, and last but not least, we have to roll with this one. So sine of pi over 4 plus cosine of pi over 4. And we said earlier that was root 2 over 2, so I'll work with both of those. They have to be the same value, right? They divided to get 1. Common denominators, that's nice. We have these invisible 1s in front. We have 2 of those square root of 2's over 2, so we really just get the square root of 2. Okay. Well, now we just have to decide absolute max versus absolute min. And you do have to label them too, but the labeling is very easy. What's the smallest? Well, that's the negative 1. This is the value of the absolute min. What's larger, 1 or the square root of 2? Square root of 2 is larger. Square root of 1 is 1, so square root of 2 has to be bigger than that. The same way square root of 3 is larger. So this guy is our absolute max. And there's the candidates test, right? Really easy. We found the critical point. We set up the candidates test by taking the critical point and the endpoints, substituted them into the original equation, found the biggest value and the smallest. Now I did say we should check this on the graphing calculator, so I'll do that right now. I'm going to pull up my calculator. We'll do our next function. You'll notice that I did restrict this function to only be between 0 and pi, and we get this guy. Look at that. 3 points that we tried the 2 endpoints. Okay, you can see pi right there, and we also tried the critical point. Notice the critical point is the largest, and it has a value of 1.414. That's the square root of 2. And the absolute min is the endpoint, which is at pi, and has a value of negative 1. Desmos just rounded poorly. Okay, looks like we're doing pretty well. That made sense with our conclusion here, so let's do one more. This is our last one. Absolute max and min values on the interval from negative 2 to 4. Okay, well, we know the first step. We need to take the derivative, and to me this looks like a quotient rule. Derivative of x squared, 2x, keep the denominator the same, minus, keep the numerator the same. Derivative of 2 minus x, be careful. I think that's negative 1. 0 minus 1, negative 1, divided by 2 minus x squared. Can we clean this up? I think we can. Let's be clever here. So g prime of x, I will distribute the 2x to both of these, I think. So we get 4x minus 2x squared plus another x squared. Look at that negative over there, divided by 2 minus x squared. And I'll continue to the right. I have a little bit of room here. We're looking at, let's see, negative 1 of those x squareds plus 4x divided by the denominator. And even going a step further, it looks like there's an x, and it's pretty common to try and make x squared positive. You don't have to do any of this. But so I'm going to factor out both a negative from both of these and an x. So I'm going to take out a negative x, and that's going to leave me with a positive x minus 4. Double check, negative x times x, that's negative x squared. Negative x times negative 4 is positive 4x. Good, okay. Divided by 2 minus x squared. Okay, I think that's about as simplified as we can make it. What next? I think we need to find our critical points. Okay. Critical points occur at 2 spots, and I am going to use space for both spots this time. They occur when g prime of x equals 0 and when g prime of x is undefined. And I was pretty confident there'd be a value that will make g prime undefined because look at the denominator, right? We know that when fractions become 0 in the denominator, the whole fraction becomes undefined. And in fact, if we want to find where a fraction becomes undefined, we should probably take the denominator, right here, and I'll zoom over a bit because my tablet's having troubles. And we're going to take this and set the denominator equal to 0, because if I find the x value that makes the denominator 0, we'll have found the x value that makes the fraction undefined. We should probably square root both sides, add x to both sides, and we found 2 equals x is what's going to make g prime undefined. There is a critical point. Let's look at a couple others. G prime of x equals 0, so we need to, well, let's just think logically. What's going to turn a fraction into 0? I actually don't need to set the whole thing equal to 0. I mean, you can if you'd like, and you'll get the right answer, but thinking logically, I think only if the numerator of the fraction becomes 0, then we have 0 divided by whatever the denominator is. That makes the whole thing become 0. So all I'm going to do here is set the numerator, which is already wonderfully factored for us, equal to 0. And then we just have negative x equals 0, or x minus 4 equals 0. So we end up with x equals 0, or x equals 4. All right, so it looks like we have 3 critical points. Let's go ahead and set up that candidates test. All right, and I'll maybe box that off. Okay, candidates test, we need to do x, and I'll leave some space for f of x over here. How many candidates? Well, clearly 3 right here. Anything else? Oh, our endpoints. -2 and, 4. Well, that's nice because 4 is already here. So actually, we don't need to include 4 twice. It's going to have the same value. I have -2, nice, 0, 2, and 4. Somewhat coincidentally, just going by 2s. And I'll extend this out, though you really don't have to. That's probably overkill. Let's substitute everything in. Okay, so when I substitute in -2 into my original equation up here, it becomes -2 squared divided by 2 minus -2. I'm looking at 4 over 4, which is 1. All right, when we substitute in 0, we end up with, I'll just keep the blue, why not? We have 0 squared over 2 minus 0, 0 over 2, that's 0. Let's substitute in 2. 2 squared over 2 minus 2 is 4 over 0, and that does not exist. Again, avoiding saying equals does not exist. An arrow is good. Just writing does not exist is good. But we try not to say equals because we reserve equals for actual values. That's why we don't say equals infinity. And then 4. 4 squared, 2 minus 4. That looks like 16 divided by -2, which is -8. Okay, and so I think we have our 4 values here. Now, looking at all of this, I think we can see our absolute max and absolute min. Turns out our absolute max occurs at one endpoint, and our absolute min, which I could spell, that would be nice, our absolute min occurs at the other. 0 is not the biggest nor the smallest, and does not exist as not even a point. So what does this graph actually look like? Well, let's take a peek. This is our last one, and if I click this, you might, if you're not zoomed well enough, be a little confused, because I see this point right here, -2, 1, right? And then you're like, okay, well, that looks kind of strange here. And then we jump down over here and we see this guy. Okay, that looks like kind of a relative min, but then you might notice that as you zoom out over here, you get this graph too. Okay, now we should notice a couple things. First, there is an asymptote, and if I zoom in, there's an asymptote at 2. Huh. Well, that's a little bit weird because it looks like the candidates test failed us. In fact, I think the absolute max up here goes up forever. It looks like it's infinitely tall. And I think the absolute min way down here also is negatively tall again, negatively low, negative infinity. And so what happened with this? Well, I think we might have forgotten one thing about the candidates test. The candidates test only applies very similarly to our extreme value theorem and most others if your function, if f of x is continuous on a closed interval. But was f of x continuous on this closed interval? Uh-oh. Notice that when x was 2, this was not continuous, and 2 was on this interval. F of x is not continuous, and so we saw actually that the candidates test here doesn't work. Now, will the AP exam try to fool you with that? No, almost certainly not. I've never seen it happen. But is it good to remember that our function has to meet certain criteria to use a test or a theorem? Absolutely. And if it was continuous, this is exactly what we do. It's not, sad day, but either way, I think you are well prepared to tackle the candidates tests and critical points.